what we're doing now is we're doing nonlinear regression part 2. And so what we have from the previous notebook is we have data where we know what's the initial velocity for the production of paranitrophenol by peroxidase at given concentrations of paranitrophenyl phosphate, which is a substrate for the reaction. And so what we're going to do now is plot the data and then do statistically robust nonlinear regression. Now, there's a wonderful tool called CurveFit we'll get to work with. And also you'll get to see just a little bit of plotting in Jupyter, in Python, and what it can do. And so in this module, we're going to import the data from a CSV file into a data frame. We're going to create a function for the equation that we're fitting to. And then we're going to use a function called CurveFit to fit the data to the function that we have. And that sounds kind of confusing. It's not surprising. We'll go through it one step at a time, and then we'll create some plots of the data. So in the previous notebook, we use this linregress function from scipy.stats from that library to perform linear regression. And so if you're just looking at linear data, that's great. And historically for biochemists, we didn't have access to nonlinear regression. When I was a grad student, we just converted everything to linear regression. We did transforms to make it linear, and then we fit it to best fit curves for linear regression. Well, now we have the power of nonlinear regression, and we can fit data. I don't know if we can fit it to any curve, but we can fit it. There's a lot of options. And so what we're going to do in this process, we're going to go through 8 steps. One is, the first thing is that we'll import the library that contain the functions that we need. And this will include CurveFit from scipy.optimize. We're then going to set up another pandas data frame with the data from the last module. Now, if you were not able to generate the data and output to this mm_data.csv file, that's already in your, there's already a version of that in your data folder. So you can use the version that's there. We're going to create independent and dependent variables for curve fitting. We're then going to create a function for the equation that we want to fit. In this case, it's going to be the Michaelis-Menten equation. I'll show the equation written out like you would in a notebook, and then we'll show how it looks in computer code. And then we'll have to have that function that accepts an independent variable and the parameters we want to fit. We'll then go forward to look at the CurveFit function from scipy.optimize. And once we use that function, we're going to extract the fit parameters from that function that generates. Then we're going to use that function to calculate Y values from the fit model to compare them to see how our data fit the optimized parameters. And we're going to do a graph of the original data and the best fit equation. And if there's time, we're gonna spruce up the graph a bit. All right. So the first thing we do was we import the libraries. And so the libraries we're using here are some of the same ones. Now, this is a new notebook, so we've got to start importing all over again. So what we imported in a previous library, a previous notebook, does not apply in this case. So I'm going to say import OS again, and that's for working with operating systems for our files and directories. We're going to import a library called NumPy as NP. Now, NumPy is a Python library that does a lot of calculations. So simple things like square roots, but a lot, trigonometric functions, those kind of things. And we call it NP just to make it easier to call when we're writing code. I'm going to say import pandas as PD. And in the last notebook, we'd had a lot of PD dot this, PD dot that. Pardon me. All right. Clear my throat a little bit. We're going to import a library called matplotlib.pyplot. So we don't import the entire library, just part of it. We're going to call that PLT. Once again, this is standard coding. If you looked at somebody else's code, if you saw a PLT followed by a period, that probably means they're using matplotlib.pyplot. And then finally, we're going to import that curve fit function. So we're going to say from scipy.optimize import curve fit. All right, now it's really important.
Hey, Paul.
Yes.
Just a curious question. There are a difference. What is the difference between making the import that you make for the matplot when you specify a specific part, and this when you say from this one import this?
Right. I'm going to turn that question over to Jessica. Jessica, are you available to handle that?
Sure. So these imports, they are different. So some of them are just import OS, and then some of them are like import NumPy as NP. When we do that, we're just aliasing NumPy for NP. And then when we have from scipy.optimize import curve fit, what's happening is that we are only importing one function from the scipy library. So when we do import NumPy as NP, we're importing everything that's part of NumPy, and we can then access that under np dot function name. But sometimes what you'll see with larger libraries, we don't want to import everything at once. So what you'll see sometimes in code is that people will import just the function or just the object that they want to use. So that's what's happening here. And really, like, the way that you can decide what you want to do is sort of like what functions you're using. But most of the time, you'll get an idea of what you should import by basically reading the documentation or seeing what other people do. But here, when we do from scipy.optimize import curve fit, it means that we are only importing one function from scipy. Does that answer your question?
Yes, and for matplotlib pyplot.
Yes.
Because
so
is it that a pyplot is a function or is a set of functions also?
It's a set of functions in matplotlib, but we don't want to import the entire matplotlib library, just that part of it, and basically to keep more memory free to do calculations.
Yeah. Okay.
All right.
Okay.
So
thank you.
we have our libraries imported there. And now I just want to explain the Michaelis-Menten equation. This is an equation that if you're a biochemist, this is probably very familiar to you, but it may not be. This is an equation we use to measure calculate parameters for kinetics in enzyme catalyzed reactions. And I'm not going to give a lecture on enzymes, although I'm a biochemist, we tend to do that a lot. But just to explain what this equation contains, VI is the initial velocity. So that's the velocity at the point when you mix the enzyme with the substrate. Vmax is the maximum velocity. That's as fast as the enzyme can go. The S in the square brackets is the substrate concentration. Km is the Michaelis constant, and the Michaelis constant is actually equal to the substrate concentration at half maximal velocity. So let's say the maximum velocity for this enzyme is 1,000. Well, Km is the concentration of the substrate that would get that enzyme to go 500. Okay, and then S again in the denominator is substrate concentration. And you know, this is, once again, this is a markdown cell, which you can do in Jupyter Notebooks. And this equation is actually created with a tool called LaTeX, which operates in markdown cells in Jupyter Notebooks. All right, so our second task here is we're going to use this equation, we need to set up a data frame that contains the data. Now, we had a lovely data frame in the last notebook, but I don't know how to pass data frames from notebook to notebook, but we have this mm_data.csv file we can use. So we're going to use that. And so what I'm going to do here is I'm going to first create a file handle for it. Data file equals os.path.join. And OS, that's the OS library, and .path, .join is telling us to connect this path together so that this notebook knows where this file is located. And it's going to be in the data folder. So that's a quote data, close the quote, comma, and then the name of the file, data.csv. And so we now have created a data file. And we're going to want to now create a data frame that contains those data. So I'm going to call it, rates underscore df. And I'm going to say that equals to PD. So I'm telling pandas, a function in the pandas library. I put the dot, and the function I'm using is the same one as last time. Read underscore CSV, open in parentheses, and data file. Now, a couple things I wanted to point out at this point is data file is not in quotes, right? It's a variable. Now, the variable contains the information in these strings, but data file is just a variable, all right? Another thing I wanted to point out is if I go into the data folder here and I click on this CSV file, then Jupyter Notebooks is able to display CSV files. So I can see the data in that CSV file. Okay, so I've got my PNPP concentration in the first column. The next column is the slopes. The third column is initial velocities. Now, let's make sure we actually got those data here. So I'm just going to type in the name of the data frame. And then I'm going to hit Shift Enter to execute. First, it'll execute the data file, this line. Next, it will create the data frame. And then finally, it's going to display the data frame if I did everything right. And it looks like I did. All right. So here we have a data frame. Now, I could go in and shift the data frame, get rid of the index file, but at this point, I'm just going to use it the way it is. And so if we're going to, actually, I'm going to stop, and I'm going to ask people to give me an indication, did that work or didn't it work? So do the red check, or the green check if it worked, and the red X if it didn't. And I'll ask the helpers to go in and see if we can get this to track down, or see if you can track down, help with the problem. The problem is more than likely the wrong kind of bracket, a space that shouldn't be there, an error in the file name, some error in the reference of what you're doing. Okay, we're safe. Well, from what I saw, it looks like most people are at the point where you have the data frame. So now what we're going to do is we need to create the variables, the independent, the X variable and the Y variable. All right. So if I look at the data frame, my independent variable is a substrate concentration, PNPP. Okay. My dependent variable, the Y data is going to be initial velocities. So I just go in here and I'm just going to call it Y data equals rates underscore DF, open a square bracket, and then quote initial velocities. Close the quote, close the square bracket. So those are our Y data. And then X data equals rates underscore DF, open a square bracket, and say P, lowercase p, capital N, capital P, space, parenthesis, open parentheses, lowercase m, capital M, close parentheses, close the quote, close the square bracket. All right, so those are our X data and our Y data are selected there. Now we want to take a look at the data and make sure it looks like it's the kind of data we expect to see for Michaelis-Menten plot. Okay, and so I'm going to enter the command plt. After this, we'll pause again just to check and make sure where people are at. So I'm going to say plt. So that's calling matplotlib pyplot and saying, look in that library to find a function called plot or plot. Then open parentheses. I'm going to say x data, comma, y data. So that tells the plot function what to look for. Then I'm going to give it in single quotes an O. That's going to give us a circle for the symbol. Then I'm going to say label equals in quotes data. And I close that quote. So in this cell, we've got the Y data defined. We have the X data defined, and both of those come from our rates data frame. And now we got this plot that's going to show us if the data look like what we expect. So if I do Shift Enter, I get the plot. And the plot that I expect to see is one where the concentrations are spaced evenly on the x-axis, the initial velocities are spaced evenly on the y-axis, and the data points form a curve that's actually technically called a rectangular hyperbola. All right, so let's do a check-in and let me know if you're seeing this kind of data, and if you're take your time getting there. Let's make sure everybody has a chance. Okay, well, I'm seeing a lot of check marks of the positive ones. So we'll proceed. All right. So let's review where we are. We've taken our data from that CSV file and put it in a data frame. We looked at the data frame to make sure it's okay. We now have defined the Y and the X data for our actual results. So these are our experimental results. And I'm going to try to make that distinction very clear because we're going to come down later to some fitted data, and those are going to be very different. We'll call those data something like Y-fit, that kind of thing. All right. So if we want to fit the curve to a function, first we have to define that function. And so the way we define functions in Python is with the def command. And you'll notice that when we actually do the defining the function, that once again, the font colors and so forth, and the bold font here for def, the bold font for return, those are clues that tells us that these are reserved words. And so the way we do this is we have def, then we give a function name, and then we provide the independent variable and the parameters that go with that equation. Now, in this particular equation, we have one independent variable and two parameters. So that's what we need for the Michaelis-Menten equation. You might have a different equation that has more than two parameters or more than one independent variable. You can do that here. Then you provide some kind of function body code to tell it what to do with the independent variable and the parameters. And then you tell it to return some value. Functions almost always return values of some kind. All right, so the equation we want to fit is a Michaelis-Menten equation, and that was here. And so the function is going to be this Vmax times S divided by Km plus S. All right. So I'm going to start with DEF. And notice there's no equal sign here or anything. You just put in the name of the function. I'm going to call this function MM for Michaelis-Menten. Notice that it shows up on my screen in blue. And then open parentheses. I'm going to put in sub conc. So that's substrate concentration. And then one parameter is Vmax. The next parameter is Km. Now I follow this with a colon. When I do that colon, that tells Python to indent the next line by 4 characters. The function is that Vi equals, so that's the initial velocity from the equation we showed you before, equals Vmax times sub conc divided by Km, now in parentheses, Km plus sub conc. So that's our function. I'm going to tell it to return Vi. So now we have a function, and notice when I hit return in my cell, after I typed in return Vi, it knew that was the end of the function. So I'm back to the left margin. So now I want to test the function to see if it produces the expected output. Now, as a biochemist, I've been looking at Michaelis-Menten data for 40 years. So I know what I expect to see. I expect to see that given a substrate concentration range, or given a substrate concentration, it'll report a Vmax and Km that reflects something about the enzyme. So what I'm going to say here is, I'm actually going to ask it to act on an entire column from our data frame. So MM, and I'm going to ask it to look at rates underscore DF, and I'm going to open square bracket, and I'm going to say PN PP millimolar. So that's going to be our X value. It's actually a series of X values. I'm going to tell it has a Km of 100 and a substrate concentration, I'm sorry, a Vmax of 100 and a Km of 1. So here's our independent variable, the PNPP millimolar from the data frame. The first parameter is Vmax, that's 100. The second parameter is Km, that's 1. So I just hit return or shift enter, and I get a bunch of data. Now, as a biochemist, I know that at the highest concentration, 20 millimolar, in our data frame, the Km is 1, so I'm 20 times the Km. So I'm going to have a pretty high rate compared to the maximum rate. I get a value of 95. Now, you notice here that the fifth item here on the, or I should say index 5, so it's actually the 6th row, has a rate of 50. Well, 50 is half maximum velocity. That's what I should see at the Km. So if I look at my data frame, I'm going to scroll up to look at the data frame now. The data from the data frame, and in index 5, the concentration of the substrate is 1.00 millimolar. All right. So it matches the Km, and so I expect that. So these data look reasonable. So I think the function worked. Okay, I'm going to stop at this, pause at this point, and ask people to check in. Is that working for you? Seeing a few more check marks coming up. And I know you're focused on the coding, and having to put these check marks in is a little bit annoying, but it really helps me to understand where we're at. All right. I think we're in pretty good shape here. So now I'm going to skip the error issue. And I'm going to talk about using curve fit. So the curve fit function is shown here. And in the function we have popt, comma, pcov. So their curve fit produces two outputs. Okay. And the input that curve fit requires is some function, some x data, and some y data. So what we have here in curve fit, this popt is the optimized parameters. So in our case, Vmax and Km. Pcov is a two-dimensional matrix of the covariance for the curve fit. And we'll use this to actually pull out some uncertainty values. Curve fit is the name of the function. The function that we're going to use for curve fitting, which in our case is going to be MM, the Michaelis-Menten function. And the X data is a data array for the independent variable, and the Y data is a data array for the dependent variable. All right. And so if we look at, here is the Michaelis-Menten function that we defined earlier. Now, if we go through here, we're going to use the curve fit function, but notice the curve fit function acts on a function. So it sounds a little redundant, but it's not. So what we're going to do here now is draw on some stuff we've already done. We've already defined, previously we defined X data and Y data to make this graph. So we've already got X data and Y data. And so for doing the curve fit, we just type in popt, comma, pcov equals. Now, we keep the names of the variables that they selected. You don't have to do that, but I'm keeping them just so I remember what is what. So then I just call curve fit. Now, and I don't have to put in like NP or something in front of curve fit, because when we imported it, we said from scipy.optimized import curve fit. So curve fit is right there at the top level for us to use. Then we open a parentheses, MM. So that's the function that curve fit is going to fit the data to. Then we've got X data and Y data. And so when I hit Shift Enter, it runs. Well, it runs if everything's correct, if we get everything in the right place. But now we want to get the results out from what we produced there. So popt, once again, is a list of optimized parameters. So it's a list. In our case, it's the Vmax and the Km. And so remember that Python starts counting at 0. So there are two elements. Popt 0 equals Vmax, and Popt 1 equals Km. Pcov is this n-dimensional array of the covariance of the parameters. In our case, since we have two parameters, it's a two-dimensional array. So we can extract Vmax and Km and the error for those. So I'm just going to type this in. I'm going to say Vmax equals Popt, open a square bracket, 0. Km equals Popt, open the square bracket, enter a 1. So those are the two values. When we execute this cell, then we'll get those results will be stored in the Vmax and Km variables. We're now going to extract the information from the pcov variable about the error, all right? So STDEV, that's going to be standard deviation, and that equals to NP. NP, now NP as in NumPy. So we're calling something from the NumPy library, and it's going to be the square root function, NPSQRT. So that's the square root of something in the parentheses. Now, in our case, it's going to be np.diag of pcov. So we're asking this diag function from the NP library to pull the diagonal from pcov, and then we're asking NP to do a square root of that. And so that's going to give us the standard deviation for each parameter. So standard deviation is actually going to be a list. So I'm going to write print and then in parentheses, F, and a quote, Vmax for this reaction. And then I'll put the curly Q brackets, and I'll call the Vmax value. And then I'm going to say plus or minus, and call the standard deviation value. Oh, you know what? Yep. Standard deviation is a list. So I'll call standard deviation element 0. Finish that with a quote. Close the parentheses. I'm going to do the same thing for Km. So print F, single quote, Km for this reaction. And then curly brackets, Km. And we've already defined that up here. Plus or minus.
Excuse me, sorry to interrupt, but I think there was a curly bracket missing in the standard deviation.
There's a what now? Oh, you're right, there is. Thank you.
Yeah, thank you.
Well, if you hadn't pointed that out, we would have gotten to see an error message and figured it out, but that was great. So STDEV square, open square bracket 1, close the square bracket, close the curly bracket, close the quote, close the parentheses. All right. If that's the only error I made and we caught it, then we should get an answer we can read. And we do. So here we have the Vmax for this reaction. Here's our value for Vmax and our value plus or minus 1 standard deviation. Likewise for the Km. Okay, I'm going to stop at that point, and looks like the responses are cleared. Please give a green check mark if that worked and a red X if it didn't. And please keep in mind that the link that Jessica put in the chat during the break will point you to a Jupyter book that contains all of this stuff. So you can go back and do it again. You can learn more about it. Now, one thing to notice here is that the answer is to 12 decimal places. Okay, we probably don't need that. And so we can change the print function, the print command here. I'm actually going to just go in here and inside the brackets with Vmax and with Km, I'm going to tell how many places I want that value to show up. All right. So I could say print, open parentheses, F, single quote, Vmax for this reaction. And then curly bracket, Vmax, and then a colon, dot, 2F. So that's going to give me 2 decimal places, plus or minus STDEV 0, colon, dot, 2F. Close the curly bracket, close the quote, close the parentheses. So if I do that, I get this statement where we only have the answer to 2 decimal places. And we can do the same thing with the Km value. All right, and how are we doing for time? All right, we need to wrap this session up by 2:45. All right. So what I want you to do is open a new cell. You can do that just by hitting the plus sign here. And go in. We'll give you 5 minutes to do this, to write a print statement for the KM plus or minus 1 standard deviation to 3 decimal places. So 5 minutes, and then we'll come back and start going on plotting. When you get to the answer, you can go ahead and why don't you go ahead and drop that in the chat window. But yeah, but go ahead and type the code that you put in. Put your code in the window. Great. Excellent. And you might look at this and think, well, gosh, that was really pretty easy. Why are you asking us to do easy stuff? And I was working on a separate problem of my own last week, and I was trying to solve a data frame problem and a math problem at the same time. And I realized I couldn't do both things at once. So I started first, I figured out how to solve the math problem. And then I figured out how to solve the data frame problem. And I had to go back to some very simple thing like counting the number of characters in a list, just to see if it would work. And once I knew that was working, I could figure out my math problem, and then I could figure out my data frame problem. And that's how I approach problems when I'm trying to solve stuff in coding. Start with something that I know will work and build on that. All right, we're going to move forward now and take a look at plotting the data. And this is where it gets fun. So okay, so we've got data that we fit, and so we're going to use those data to actually give us a look at what we've gotten. So what I'm going to do first of all is I'm going to use the parameters that we got to generate the predicted data points. All right, so I'm going to call this fit_y. And so this is going to be a list. And I'm just going to take that's our function. Give it the x data, the vmax, and the km. So those are the parameters we determined. And so that's going to give the y values that we're going to use. And now we're going to graph our original data with the fit data. So I'm going to say, first we do the experimental data. Okay, there's a question, how can we print the fit equation? Well, we're not going to print that. We're actually going to take the data or the results we got from the fit equation and import it here. You'll see. So let's say plt.plot. This is exactly the same code we used above. X data, comma, y data. So that's our x and our y values, comma. Then I've got a single quote with an O, so that gives us a circle, comma, and label equals, in quotes, data. Close that. So that's part of our plot. So this is the experimental data. And then the next line, plt.plot. We use the same x data. We'll use y data now. And I'm just going to use a dash. So we're just going to get a line here for the appearance. And I'm going to say label equals fit. And if I entered information properly, when I execute this cell, then we'll see a plot. It worked. Okay, I want people to check in. Did that work for you? Are you able to see a plot that looks like this? Few people getting the plot to work. That's good. Good. I'll wait a few more seconds here. All right, so when you look at this plot, what do you notice? What would you like to change about it? This open question. So feel free to answer. Maybe I'll have you put the answers in the chat room. That'll make less chaos. So what would you like to change about this plot as you look at it? Axis titles, okay, we can do that. A best fit, okay, what about the best fit line, Nelson? Smooth it, right, exactly. All right, we're going to smooth the line, and then we're going to add some titles. Now, what we have here is a curve based on 11 data points of actual data and 11 data points of fitted data. Okay, and you can see that the actual data falls almost exactly on the curved line. which is fine. I think I'll go back and change the book so they're a little more scattered, or change the data so they're a little more scattered. But in any case, but you also see that the line is a bit herky-jerky. Okay, it's not smooth. And so what we're going to do now is we're going to create a smoother curve. I'm going to call this, we're going to have smoother data. So I'm going to say X, or smooth X, equals, now we're going to call a function from NumPy. So NP dot tells Python we need to call a function from NumPy. The function is called linspace, Linspace, and it's a function, so we follow that with an open parentheses. And we tell it, I'm going to tell it to go from the minimum X value to the maximum X value and generate 1,000 points, 1,000 X values. So the way we do this, once again, is a NumPy function, np.min of X data. So it looks at our list of the X data and it takes the minimum value. And np.max, np.max of Y data. I'm sorry, X data. We want to go from the minimum to the maximum of the X data. And we want 1,000 points. All right. So this gives us an X value range of 1,000 points. We can make it 10,000 or 1,000,000, but we don't need to. So that's going to give us our smooth X. So now we want smooth Y. Well, we want that based on our fitted parameters. So I'm going to say smooth Y equals so that's our function, times smooth X. So that's the 1,000 points plus, and I'm sorry, smooth X comma Vmax comma Km. So this is going to be our Y values for the 100 points. Okay, so that gives us our smooth X and our smooth Y. So let's go back and plot again. So we take, you probably want to just go to the cell above and cut and paste, but I'm actually going to put it in by hand. So I'm going to say plt dot plot. And then in parentheses, X data, Y data. I'm going to make the points, the O's, I'm going to put a B in front of the O here so that it's a blue circle. A comma there. I'm going to say label equals data. And then I'm just going to put a comment on the line, put a pound sign, and then say plot of the experimental results. Then I've got another line. I'm going to say plt.plot. And this is new. This is going to be the smooth X, smooth Y, and I'm not going to give it, I'm just going to give it, tell it to make them red. So it's going to be red dots. And in this case, I'm going to say label equals fit. Yeah. And it turns out I can use single quotes or double quotes as long as they match. And so I'll say this is plot of the fit data. I'm going to go in here and say plt.legend. And so that actually shows a figure legend. So if I entered this correctly, oh, the question is, what is BO? So the B tells it to be a blue, and the O tells it to be a circle. So if I execute that, you can see that we have this lovely smooth curve now. So very nice feature there. And I'm going to ask people once again to give the red check or the green X to indicate if you're able to do that or not. All right, looks like we got one or two folks having a little bit of a struggle here. So you may need to ask somebody to go with you to a breakout room, or just put a question in the chat. Maybe we can get it resolved that way. But in all likelihood, it's probably most of the time it's just an error in typing. You know, I put the wrong thing in. All right. So one of the things that's fun to do with these plots now is to add some more information on the plots. And oh, this is funny. I'm working off my notes and I don't have the notes. I'll see if I can remember this. If I get it wrong, we'll have to look it up. I believe it's plt.annotate. You know what? I've got another source. I'm going to go to my other source and bring it up. Let's try this. plt.annotate.x-axis. And I'm just going to say, this is just PNPP concentration. So square bracket PNPP, close the square bracket, open parentheses, lowercase m, capital M, close parentheses.
Paul, what are you trying to do? Are you trying to label the x-axis?
Yeah. Oh, should it be x-axis?
It's just plt.x label.
Thank you.
Yeah.
Like I said, I don't have my notes in front of me. So if we do that, you get an x-axis label there. All right. And then if you want to do a y label, you do the same thing. And that's going to be initial velocity. And so we have axes labels. And it's possible to go further and to locate equations, to put the best fit equation and so forth in here. You can actually add that to the screen using an annotate function in there. Any question? Well, let's go through, have people check in. How do you clear the check marks, Jessica?
You can click clear all reactions. I'll do that for you if you want.
Yeah, where do I find that clear all reactions?
It's on participants, the 3 dots. It's actually clear all feedback.
Okay. Yeah, if you would do that, that'd be great. All right, now, give us the green check mark if you got that to work, and the red X if you didn't. Okay, there's a question in the chat. Without the 1000 point, the smooth X and smooth Y data, the fit curve is just connecting the experimental data, correct? No, that's actually not correct. What's going on there is the fit curve in this plot is connecting the predicted value at each of these X values where there is a data point. Now, it turns out the data are pretty close to the theoretical value. There's not much scatter in the data. Huh. Well, that's funny. I just held my hand up like this and it raised the hand for me without me telling it to do so. Interesting. Other questions? All right. So you've seen how to do a smooth curve, and we do provide kind of a take-home exercise. And we're not going to take time for this today, But we're going to take the take-home exercise is basically to take the chymotrypsin data that you would have created in the previous notebook and fit it and create a plot here. So it's a similar exercise. You have to do a few things differently.